I'll introduce myself. I'm Paul Suhler. I work for Kioxia Corporation, and I'm also the chair of the IEEE Security and Storage Working Group. What I'm going to be talking about today are changes in some encryption algorithms and then various other algorithms that are coming up that are going to affect everybody's products. The main things I'll be talking about are things that are coming in the IEEE 1619 standard, which defines the XTS-AES algorithm, which is used by virtually all self-encrypting drives. Talk about some of the post-quantum cryptographic algorithms that have been defined and are finding their way into the ecosystem. And talk about some trends in sanitization techniques. One of the big things that the IEEE SISWG, as it's abbreviated, works on. And I'll also talk about various standards and how they all interact, and give you a call to action. I see lots of friendly faces here, so I expect lots of questions and harassment, so please don't disappoint me. So first off, IEEE 1619, standard for cryptographic protection of data on block-oriented storage devices. This is what's used by, I suppose, virtually every self-encrypting drive that there is. It was originally defined in the Security and Storage Working Group. The current version of the standard that's out is from 2018, but all the way back to the first version from 2007, it defines what's called the XTS-AES encryption mode, and that is approved for use in FIPS 140-3 certifications. It is the AES encryption standard, but it has a special mode of operation so that you can encrypt logical blocks individually without having to re-encrypt adjacent blocks. So here's kind of the ecosystem of requirements. FIPS 140-3 is what people have their devices certified to, including self-encrypting drives, self-encrypting tape drives, et cetera, et cetera. Now that depends upon special publication 800-140C, currently in revision 2, and that defines approved security functions. And one of those that's listed, it points to SP 800-38E, which is recommendations for block cipher modes of operation, specifically for this XTS-AES mode of operation. Currently, so we have 140-3 points at 800-140C, which points at 800-38E, which adds a few more requirements on top of XTS-AES as defined in 1619. NIST found a problem with with XTS-AES and got in touch with us. A lot of the credit for that goes to Eric Hibbard, who's also a member of the group. He's been very big on keeping the different pieces of the different organizations that do standards working with one another. When IEEE publishes the new 1619 to fix these problems, then NIST is going to update 800-38E to point to this very latest version. So what's the problem? Well, the previous requirements are around what's called a keyscope. A keyscope is basically the amount of data in a device that is encrypted with a particular key. In this case, we're using the Advanced Encryption Standard, AES, which uses 128-bit blocks. The latest version of 1619 from 2018 allowed up to 2 to the 64th AES blocks in a keyscope, and earlier versions were more lenient. So what does that mean? That is, it would allow us to encrypt up to 256 exabytes with a single key. That's a problem. Would anyone care to guess what the problem is when you have lots and lots of ciphertext with one key? Well, basically, the more data you have with a single key, the better chance an attacker can take all of that ciphertext and drive the encryption key and then read the data, which is obviously something that can make you subject to a lot of financial penalties if you release customer information that way. So there are a couple of analyses we were given by NIST when they came and spoke to us about this. A petabyte encrypted with one key would give you about a 2 to the minus 37th chance, about 8 chances in a trillion of, on a particular try, being able to get the key. Guess what the key is. And I'm sorry, I shouldn't say guess because there are more sophisticated cryptologic methods and I don't pretend to know anything about them, but you can do more than simply randomly guess keys. An exabyte, 1,000 petabytes, would give you a success rate of 2 to the minus 17, which is 8 in a million. And if you have lots of machines and energy to expend trying to decrypt data, this is, well, that's quite doable. So NIST suggested that we reduce the size of the key scope, place stricter requirements on the maximum amount of data you can encrypt with a single key. So where the requirements are going in the version of 1619 that we're trying to push out, hopefully over the next 2 months, the key scope shall not exceed 2 to the 44th blocks, which is 256 TB bytes. And then we have a looser requirement, a should requirement, that we should not, I shouldn't say it's looser because it allows even fewer bytes, fewer blocks to be encrypted, so that we recommend that the keyscope not exceed a terabyte. Okay, how big are the current, say, SSDs on the market? They're already well beyond a terabyte, so this is potentially already a problem. There are other little details about data units. I don't need to dive into that right now. That's peculiar to the algorithm. If you really care, you can look at the standard. But the point is that drives have now gotten so big that this has become a problem. And we need to tighten down the amount of data that can be encrypted with one key. Yes, Randy?
So is that encrypted at one period of time, or is that encrypted ever?
That is encrypted and available on the drive. For example, assume the attack is that somebody's going to pilfer this drive. They don't know what the key is. They can't unlock it. But they can read every bit off of the drive, put it into their big machine, and proceed to crunch away at it to try to figure out what the key is, and then read all of the data. Sorry, it was just a clarification of how often, yeah, okay, go ahead. Randy, why don't you answer? Is that turned on now?
It is now.
Can,
It is now.
no? Try.
It's a big switch.
Hello?
No. Again, say your question. Okay, Randy's question was, is this limitation at any given time, or is it over the entire use of the key? And that's why I said it's the amount of data that's available for somebody to steal and use to decrypt or to derive the key. Okay. Yes, Dan.
One clarification you might want to add on that. It's not just mapped data, it's unmapped.
I'm going to get to that too. Assume the attacker can get the entire device and get all of the accessible, right? Even if it's not accessible over the interface.
One more. The key scope is definition is key and initial tweak.
Yes, and I don't want to go into that. I've been having offline discussions and some of the technical definitions of the definition. Well, John is asking, what is the key scope? And it's something I really don't want to go into. There is a key scope identifier that is composed of an initial tweak value, and I'll show you what that means later, as well, and then the amount of data that's encrypted with the key. But for our purposes, the key scope is the amount of data that's encrypted with a single key, without regard, and we don't need to worry about other little details like that. Okay, so this shows what we have. Down at the bottom, we have each of these squares is an AES block, 16 bytes. And then let's divide those up into logical blocks. So that's one logical block. Well, if you've got a 4K logical block, then there are going to be 256 AES blocks in that logical block. Now, those, as you see, go up to the key scope at the top. All of these throughout the entire device are comprise the key scope, as you know, assuming a single key. So I just wanted to show you here the relationship between the AES blocks, the logical blocks on a block storage device, and then the key scope. So we're now going to go a little bit too deep beyond what you really need to know to get the point of this, but this is what AES encryption looks like. At the top we have P, which is plain text, unencrypted data. One AES block at a time flows through the engine and produces C, ciphertext at the bottom. We have a key coming in here. Now, AES was originally defined with three varieties in which we had 128-bit keys, 192-bit keys, and 256-bit keys. One of the new requirements coming out of NIST deprecates the smaller keys. So if you're going to be implementing this algorithm and intend to sell it to the government and you want to pass 140-3 certification, you're going to have to be using 256-bit keys here. Now, the other little pieces of this is part of the key that's used here. There's a second part of the key. It's key 2. You see it up at the top. That is used to encrypt a number I, which is essentially the logical block identifier. That's the way most applications work. So what you see is you have the numbers starting at 0, 1, 2, 3 up to whatever. That is encrypted with AES using key 2, the separate part of it. Then there is a modular multiplication that comes in. The way that works is you remember that there may be, say, 256 AES blocks for a single logical block. Well, each of those has its own indicator of its position in that block, 0 up to 255. That number is used to produce a modular multiplication, and then that, which is all dependent upon the logical block and the position of the AES block within the logical block, it's used to XOR the plain text coming in, then that's encrypted, and then it's used to XOR the ciphertext going out. And so it's, okay, to say that again, the logical block produces this number T right here, which is XORed with the incoming and outgoing ciphertext. Decryption operates similarly, ciphertext in at the top, plain text out at the bottom. We had a question?
For both the encryption, do we need to have the same size of key, or we can have like one side 56 and another side?
No, the question was whether you have to have the same key size, and the answer is yes. You have to use the same key. This is what's called a symmetric encryption algorithm. Use the same key for encryption as you do for decryption, but they've got to be the same.
What I'm asking is like there are two different encryptions, one from here from key 1 and
Yes.
key 2. The key size should be same.
Okay.
For encryption. I'm not talking about it.
Right. Okay, let me make sure I understand your question. Do key 1 and key 2 have to be the same size? I believe so. Every use of AES under the new requirements will have to be 256. So that means you've got a 512 byte key used for encrypting. You know, half goes in here, half goes in up there.
And for decryption, we are using the asymmetric encryption.
Yes, they're the same keys used. Yep, same keys. somewhere in here, well, up on that first line, see key 1 is key 1 appended, or key 2 appended to the end of key 1. It works the same for encryption and decryption. Okay, so what does it mean to people who are building devices that use this encryption, and those who will need the devices and or host code? This is going to affect all upcoming implementations. Like we said, previously a drive was not practically required to have more than one key. But now, even with the more lenient requirement, you will need a separate key for at least every 256 terabytes of data. So a 32 terabyte drive will need to keep 32 keys. And you can't lose any of these because you would not be able to decrypt the data. So you really have to maintain those as long as the encrypted data is there. Randy, you're shaking your head.
Why does it need 32 keys?
Okay, why does it need 32 keys? Because, let's see. I'm sorry, I got halfway through two different examples here. When I originally wrote this, I was using the stricter, or well, the recommendation of 1 terabyte of data per key. And that's when it makes sense that a 32 terabyte drive would need 32 keys. I failed to update the slide. Sorry, there's incoherence between those two lines. I'll fix that before I upload the final version. Anyway, the drive, as it encrypts, has to track how many AES blocks have been encrypted with each key. I'm saying AES blocks, but you can do the computations in bytes. It's the same effect. And what gets interesting is the drive has to now track which of multiple keys was used to encrypt each logical block. There are a lot of different ways to do that. We don't know if NIST in their future 140-3 certifications is going to push vendors in one direction or another. But let me show you a little bit more about that. Okay, here's the worst possible way to do it. This is conceptually what happens. You want to rewrite logical block number n in the middle up there between n-1 and n+1. Well, the brute force way to do it, all of those blue boxes are encrypted with key A. So you decrypt logical block n, there it is in white in the next row. Then you rewrite that with the new data that's just been given to you in a write command, and then you encrypt it. Except key A has already reached its limit. The key scope for key A has reached, whatever, if it's going to be 256 terabytes encrypted or whatever. So at this point, you have to get a new key and re-encrypt with that key. Now, this can be pretty inefficient because if you want to, when you get any given logical block address, you'd have to look up which key it was encrypted with, and that can take a huge amount of resources. So this is brute force, very inefficient way to do it, although it's effectively what has to be done. There are some other implementations. If, for example, you're using a NVMe device and you have multiple namespaces, perhaps you can have one keyscope per namespace. That's really not a big departure from some current implementations. You may be familiar with Trusted Computing Group's Opal spec, a feature called configurable namespace locking. And what we had done there was allow either the entire device can be encrypted with one key, or each namespace could be encrypted with a different key, or even different ranges of logical blocks within a single namespace can have their own key. I think the only limit is that, at least within the TCG spec, the device is not required to support more than 1,024 different keys, which potentially is a problem. But what they've done there is there are mechanisms in place, and designers understand these, of how they can associate the key with, for example, the namespace. And I will get to Dan's problem in another minute here. So, like I said, just keeping a current key and then flipping over to a new key when you fill up the first one is pretty inefficient and very resource intensive to track. So what are the other places you might have data? Well, once you have encrypted some data, it's gone for one logical block, and then later that's overwritten. Typically the way SSDs work is that media will be swapped out. The translation from logical address to physical address is going to point to the new data that's encrypted. However, somewhere sitting off in unaccessed media is the old value of that logical block encrypted with the previous key. So it's not just the logical blocks that you can read at any given time over the interface that count against the keyscope. It's also the ones that are sitting on this deallocated media. So it's not necessarily, you may have, for example, if your limit on the keyscope is going to be a terabyte and you have a terabyte namespace, you are really going to have to end up with more data encrypted for that namespace than simply the amount you can read, the 1 terabyte. There will be this other media that have been, say, part of over-provisioning. Another idea is that I hope people here have heard of sanitization. One of the ways of doing this with a self-encrypting drive is all the data is encrypted. So if you want to sanitize the device, you simply erase that key, override it with some random numbers. And then in principle, because that key never existed outside the device, it would be impossible to recover. And then you can't read any of the data at all. So one potential problem now that we've got multiple keys in the device is when you actually generate the key that's used in the encryption engine, perhaps what you should do is have a single low-level key, and that any key that comes into the engine is XORed with that very secret key and then plugged into the engine. Then if you can erase everything, effectively neuter all the keys at one time by changing out that one special key. That's an implementation detail that some people may choose to do differently. This is not only a problem, well, XTS is not only used for device-based encryption, it can be used for a host that encrypts data and writes it to the drive. Now, when I say a host, yeah, it may be, Intel processors have AES support in their instruction set. It might be encrypted up in the computer. It might be an intermediate encryption engine that sits in the middle of the cables from the host to the encryption engine to the drive. So in that case, the drive would not be doing the encryption. The host, in whatever form, is going to be doing that. Okay, what's the threat here? That an adversary may be able to snoop that transmission of data to the drive, build a big database, and then quietly go off and try to crack the keys. They've got the data, and they will try to derive the keys. So what this means is if you're using XTS-AES in a host, the host has to be responsible for tracking the keyscopes. There is no way the drive would have any knowledge of what the keyscopes are. It cannot police that. Responsibility goes to the host. How many people have heard of Keeper.io? Okay, good. I knew some who had to know it, and others, I knew there would be others. But for those, the other half of the audience, Keeper.io began in NVM Express as a way of encrypting a range of logical blocks with a different key. The example that was given at the time, one was that, for example, you have one file, a certain range of logical blocks, certainly not near the capacity of a drive, but that may contain information on one person. And you may receive a court order to erase any data for that one person. Well, how do you do that? Well, the best thing then is write each file with a different key. And you keep those keys not in the drive, but they live in a key management appliance. And wherever that data is, whenever you write a file for that person, you would pull the appropriate key from the key management appliance, plug that into, or inject it, the term is, inject it into the drive, and then specify that key inside an actual write command. And it works the same way for read. You specify which key that range of logical blocks was encrypted with. And for what it's worth, that injection mechanism was defined over in the Trusted Computing Group's storage working group. So it's two pieces, the part in NVM Express and the part from TCG. One point of this is that if you power cycle a drive, like when you unplug it, stick it in your pocket, and sneak it out of the data center, it loses power. Any of the keys that have been injected are kept only in volatile memory, and so they're gone. So in principle, everything, all the data, all the encrypted data is protected. However, in this case, there's no way for the drive really to tell, or no way of any reasonable complexity for the drive to tell which key, actual key, was used to encrypt any given piece of data. So it cannot police the size of the keyscope. Again, for the key per IO functionality, the host has to keep track of the keyscope, how much data was encrypted with each of its keys. So to wrap up part of the talk on 1619, we have a call to action. If you're a drive vendor, you need to analyze your new designs. Find a way to implement multiple keys, find a way to track the keyscopes on each of those. If you're a host software vendor, if you're using key per IO, find a way to track keyscopes. If the host software is directly implementing XTS-AES, then implement tracking of keyscopes there. Okay, before I move on from 1619, does anyone have any questions? Okay, you can always ask again at the end. Yes, John.
I'll go back to, it's pretty darn important to figure out if keyscope includes the tweak or not.
Important. Yeah. What John's saying is it's important to understand if the keyscope includes that tweak value that's put in there. And I don't think that is specified my understanding is, well, okay, key 2 is used to encrypt the tweak itself. That's part of the larger key. So I would say that should be the answer to your question, or am I misunderstanding where you're going with that? The amount of, are you asking whether, let's back up. Are you asking whether the encrypted data that comes out of this left-hand encryption, are you saying that amount of data that comes out is counted separately for the data? Okay, go ahead.
Does the keyscope, in effect, relate to the LBA or to the entire namespace, which uses the key space?
I'm not, okay, tell you what, would you like to?
Okay. So if the tweak is included,
okay, you're asking whether the tweak value I is included in the amount of data that is encrypted. Is that your question? Yes, that's the question. I think not. It's not really. Eric, do you have an opinion? You were there when you first created 1619, and I'll repeat your answer.
The short answer is we've always focused on the plain text going through and not the.
Okay, so Eric Hibbard, like I said, was in on the original development of 1619, and the 1619 from 2007 up through the current one, they only look at this amount of data, the actual ciphertext that comes out of this computation, not the tweak value that goes in.
Yeah, the tweak
Yes,
affects what the key does.
correct. The tweak affects what the key does.
When you're doing the computation,
Yes,
to look for the birthday effects to get to the other stuff,
Yes.
that does not account for the tweaks. And so that provides us a little more coverage, but we don't really scope that.
right. So, and part of the point is, remember I said that this so-called tweak value I is usually in many implementations the logical block address. To make it harder to guess that, that's the reason it's encrypted.
Well,
And-
it's not so much more, it's not hard to guess.
Correct.
It turns it into a multivariable rainbow table because there's a different value for every LBA.
Okay, right. So what he said is there is a different value coming out here at T for every LBA. Multi-value rainbow table, I am not familiar with the terminology, but probably we don't have to dive into that here. Okay. Okay, so let's move on past 1619. I do have a few other things I'd like to say in the 20 or so minutes remaining. Let's talk about post-quantum cryptographic algorithms. 30 years ago, a problem popped up that at that time was hypothetical. A mathematician named Peter Shor came up with an algorithm that a future hypothesized at that point quantum computer could use to find prime factors of integers in a polynomial time, not in an exponential time. Now, this would break asymmetric encryption algorithms that are at the heart of a lot of internet security, or in particular, public key infrastructure protocols. This includes RSA, the Rivas-Shamir-Edelman algorithm, finite field Diffie-Hellman key exchange, and Diffie-Hellman key exchange using elliptic curve cryptography. All of those can now be, when we get a, you see this line down here, cryptographically relevant quantum computer. Those algorithms can be broken. And that's the interesting thing. I don't remember the precise number of Q bits, quantum bits that are required for a particular size key for any of these algorithms. We're not there yet, but they are coming. Their work is progressing, and so what's happened is that NIST has tried to get out in front of this potential catastrophe by coming up with new algorithms. Some quantum resistant, or also called PQC, post-quantum crypto, algorithms have been developed and implemented in commercial products. In fact, one algorithm was developed and then it was found to have problems, so it was withdrawn. Okay, so here's some of where I'm going to try to lead you through. The US government has established deadlines for support of PQC algorithms and products they will buy. These algorithms are listed in the CNSA 2.0 suite, and I'll show you what that means in a second. But PQC algorithms are appearing in other algorithms besides the CNSA. Commercial National Security Algorithm Suite version 2.0 has a timeline for products that are to be procured by the government. You see the crosshatch parts of these are the CNSA algorithms need to be added as an option and tested sometime during the range of time. The solid ones indicate that the CNSA algorithms will be the default and they'll be preferred. And after the end of the line, the circle, you can't see it really, it's a circle with a check mark for each of these. After those dates, they will be required, products purchased by the government that fall under this will be required to implement these algorithms and nothing else. Some of the earliest ones that'll be required to put in are software and firmware signing, the top row. The next, also having a deadline of 2030, is traditional networking equipment. And by 2033, web browsers, operating systems, other niche equipment, and custom applications should all be using the CNSA quantum resistant algorithms. So this can be kind of a problem because 2030 is 6 years away. Products are often expected to have a 7-year lifetime. So if you want to sell something to the government that is going to live out its 7-year lifetime, then you basically have to have PQC implemented and certified 7 years before that final deadline. So if there may be some algorithms, or sorry, some products that implement those already that will make, say for firmware signing, they will make the 2030 deadline. But it's this long lifetime of the products that they purchase that should be providing a sense of urgency about getting these algorithms into your products. Yes, the question was about Shor's algorithm, about prime number factorization.
But does that apply to ECC?
Error correction codes? I don't think error correction. Elliptic curve. Yes, yes. One of those algorithms was Diffie-Hellman for ECC, and yeah, I know elliptic curve was the big thing about 10 years ago or 15 years ago, but it is subject to, it depends on factorization. I can't write the equations for it, so I don't pretend really to understand it. But yeah, now I don't know. I guess the question is, are there any variants of ECC that are used for symmetric encryption, or is that only for asymmetric encryption? I'm not sure. It is used for symmetric encryption? Okay, all right, all right, so ECC, according to a couple of folks in the audience, insists that ECC elliptic curve cryptography is only for asymmetric algorithms. They're not something you would want to use for actually encrypting the data that goes onto a device, for example. Okay, so as I said, CNSA applies to the national security system owners and operators, and by derivation to the vendors of equipment that they buy. Here are the algorithms and standards that are part of CNSA 2.0. This is your reading assignment. FIPS 197 made a change to AES. Remember I said that it came originally with 3 different key lengths? FIPS 197 is restricting that to 256-bit keys only. 197 has been out for 2 or 3 or 4 years, I think. Also FIPS 203, well, let's see. Okay, 2 that just came out in August, I believe. FIPS 203 is originally it was called Crystal's Kyber, but it's been given the government speak name of Module Lattice-Based Key Encryption Mechanism Standard, MLKEM. FIPS 204 that was approved the same day was Module Lattice-Based Digital Signature Standard, MLDSA, formerly known as dilithium. So those are some of the newest things that popped up. There is also, I guess I didn't mention it here, there was a FIPS 205, but it's not part of CNSA 2.0, even though that other algorithm is defined. Another one that came out a couple of years ago is FIPS 180-4, which is secure hash algorithms. I'm sure you've all heard of these, but now the SHA algorithm is restricted to 384 or 512-bit implementations. There were SHA-1 and SHA-2 had much smaller keys required. Finally, let's see, SB 800-208, signing firmware and signatures for firmware and software. There are 2 algorithms defined there that are now approved for use in this suite, LMS and Leighton-Macaulay signature and the extended Merkle signature scheme. So that pretty much rounds out the major algorithms that are listed in CNSA. So like I said, this is everybody's reading assignment. As we said before, RSA, Diffie-Hellman, and elliptic curve cryptography have been deprecated because, Quantum computers can relatively rapidly factor products of large prime numbers. The deadline is the final transition to quantum-resistant algorithms for these national security systems is supposed to be complete by 2035. There are details, and there's a link in here when you download the presentation, a link to a paper that gives the details of these. Yes, John.
Heckle a little bit more.
Okay.
205,
Yes.
which is the stateless hash base, I believe is also in this list. Stateless hash-based signatures, is that? Yes. Right, that's FIPS 205, but it was not put into CNSA 2.0. Yeah, okay. Yeah. Let's see, okay, this just sort of summarizes what I already said. List 203, 204, here we are, 205. It is not part of that particular government requirement. Things that are coming up is FIPS 206. It's a fast Fourier transform-based digital signature scheme. We have yet to see the first version of the first draft of that standard. And I've been warned that I have about only 10 minutes remaining, right? Okay, so let's talk about transitioning, because you can't, obviously you're going to have some devices talking to other devices, and they're not necessarily both going to implement the PQC algorithms. So there are hybrid algorithms being defined, mostly over in IETF, the Internet Engineering Task Force, that will allow PQC and non-PQC devices to interoperate during this transition period. They're looking at things like certificate signing, key exchange for transport layer security. Let's see, here are a list of 5 internet drafts. None of these have been published and made it the status of an RFC, but these are some of the ones that are in the works right now. And again, those are links so you can pull up the latest version from the IETF website. So what have we seen? Up until about a year ago, most of the work was on specifying the PQC algorithms. Now we're shifting the focus into modifying the protocols to use PQC algorithms, some of them SPDM and DICE and others. Vendors, this is new stuff, but the deadlines are coming rapidly, so please don't assume you would be given a pass if your device would be given a pass if it doesn't implement these. Talk to your security labs. Let's see, I mentioned DMTF is where the security protocols and data modes standard comes from. Version 1.4 is probably going to add 203 and 204 by early next year. Trusted Computing Group has what's called the Device Identifier Composition Engine. It also has a standard, its core architecture standard. There's a family of Opal standards. There's an enterprise standard, and then finally key per IO. All of these are potentially affected, and the work will be done in those standards groups. Okay, to move on in the last few minutes here, sanitization, making sure that nobody can read your customer's data if your storage device goes out the door. And there are various scenarios there. In IEEE, 2 years ago, we defined standard 2883, which gives 3 techniques for purging user data. So this is really probably more than I'm doing this for vocabulary. There is cryptographic erase, in which all the data on the device is encrypted, and cryptographic erase eradicates all the encryption keys. This is the fastest one. There's one called block erase. Really, it applies to SSDs where you can erase an entire, say, chip at a time. The time depends on how many media erase blocks can be erased at the same time. And then there's the worst of all possible worlds, which is overwrite, in which you actually go back and rewrite every logical block on the device with a separate pattern. This is it's a holdover from hard disks, and it's really the slowest technique. If you're working with NAND-based media, it'll increase your write amplification, so it's not something you want to do. Okay, some of the new things that have popped up. The latest standards from NVMe have what's called post-sanitized media verification. You need to be able to prove that the original customer data is gone. How do you do that? Well, it can be a problem with crypto erase and block erase techniques because those tend to blow away the error encryption on the media. So if you try to read it, you will get a read error. We've defined a way there in which you can read data that comes off of the media. And if you want the details of that, go see the NVM Express base spec and the NVM command set spec. Another thing we're working on is purging, removing the data in a single namespace. Right now, crypto erase is the only generally applicable technique. Part of the problem is you may have data from different namespaces that in some parts of the drive are intermingled and you can't go chase those down. But if they've been encrypted at that point, you blow away the key, then you've maintained your security, even though it's intermixed with other namespaces data. Main part of that is the other namespaces in the device have to remain usable, reading and writing, during the time you're sanitizing the target namespace. Other things, large storage devices. Obviously, overwrite and block erase take a long time, so the bigger the device, the bigger the advantage of cryptographic erase. We have distributed and virtualized storage systems, something we're working on a new standard, 2883.2, for sanitization of those. You may have one user's data scattered across many physical devices intermixed with other users' data. How do you erase that? Cryptographic erase can help you avoid the need to purge data that's scattered out on multiple devices. Yes, I'm sorry, I meant to say, yes, dispersed namespaces is an example of that. That's a concept from NVM Express. Okay, sanitization and sustainability. Organizations that have highly sensitive data still insist on shredding their devices. They have found instances, we had someone come and talk to some of us during FMS last month. They found instances in which a device says it's sanitized and they pulled user data off. I don't know if they had to disassemble the device and look at it in a lab or they could simply read the device, but they have no confidence in the actual sanitize command, even if it is crypto erase. So what they will do is shred the devices. Now that creates a lot of pollution, and you'll be hearing, I believe John Michael Hands will be talking about this later this week. What you'd like to do is take the device apart so you can feed the different components into different recycling streams and produce less of a mess that has to be cleaned up. One final point though is data eradication is very difficult to prove, and proof in the mathematical sense, with that kind of certainty. And that's been an impediment to adopting methods other than destruct, which is shredding a device or actually, more often, actually melting down the media. Because if you shred a device, well, bits get smaller and smaller. How small do you have to shred? Just melt the whole thing. In fact, we saw optical storage on sheets of glass earlier today, and I can't think of any way to sanitize those, either crypto erase or melt them. So, okay, the rest of this is not urgent. You can read this off the slides offline. ISO-IEC is currently points at the IEEE standard 2883. We will have it pointing at two new standards that we are working on. I've already mentioned 838E is going to be revised to point to the new 1619. And CNSA is going to use content that are defined in various NIST standards. And NVM Express, new standards do point to the 2883 standard. So there's this whole web, and you can chase that down. I mentioned 2883.1, that's recommended practice for doing storage sanitization. We're working up another one, 2883.2, that will give recommended practices for sanitizing data in virtualized and cloud storage. And there are others we're working on.
but I'm not going into that now. So, call to action. Understand which of the standards apply to the products that you sell or that you buy. You need to evaluate the changes to your product specifications and to your purchase specifications to make sure that you're going to be implementing this in your end products. Implement those changes, and then finally, please, if you see problems, or even if you don't, bring us your expertise. Come to these standards groups and help us develop standards that are really going to be relevant to what you do. So that's the end of my talk. Do we have any more questions before we go for drinks? Coffee. Or tea. Okay, well, thank you very much. I appreciate your time. I hope this is helpful.